two professors, two postdocs, and a PhD student joined forces a few years back and created one of the most flexible RF transceivers I've ever laid my eyes on. At full blast, you can expect 20 megabits a second, but you also have the option to slow right down and get super groovy in the sub-microwave domain. Today, I'm talking with Dr. Frederic Nabki of SPARK Microsystems. I love what they're doing over there because of their roots. They are true engineers, and their documentation shows it. It is so top-notch. I felt the need to tell them something like 3 times during this interview. I can't wait to share this company with you. We're going to get you up to speed with who they are, compare their ultra-wideband RF protocol to Bluetooth, talk about how to take that chip and run with it, and find out what the future holds. Frederic, thank you very much for joining me in the studio today.
Thank you, Elliot. Happy to be here.
Look, we featured you on IPXchange previously, but just for the sake of myself and our subscribers, would you just give us a short rundown on what you do there at SPARK?
Yeah, SPARK Microsystems makes a wireless transceiver that has unique capabilities. It's super low latency, fairly high data rate, ultra low power. It operates in the ultra-wideband spectrum, and we offer that transceiver with an SDK for people to use the technology in their use cases where they just can't get what they want from Bluetooth or other wireless technologies.
Right, so we say low latency and high data rate. So first thing I think about is Bluetooth and low power. The first thing that I think about is like Bluetooth stereo audio. And I sort of previously looked into methods of streaming high quality audio using SoCs like that, only to find that they're very complicated to use or outdated. Now, I've been on your website, and later I want to talk more about the sort of engineering experience of adding one of your ICs into a design. But first, in our last interview, you showed us a guitar amplifier and a drum set demo, and that sort of highlighted that latency part you were talking about, and that's like a real advantage that it has over Bluetooth. So on the topic of Bluetooth and audio, what are some of the advantages that your transceivers have over a Bluetooth audio approach?
Well, when it comes to audio, we find it very palatable for customers to understand the technology's capabilities because audio is a very, I would say, direct to the senses experience.
Yeah.
So with Bluetooth, it's very quick that you notice that there's a delay that's not negligible. Anybody, engineer or no engineer, technician, no technician, and layman knows and notices that there's latency, notices that the quality is not really, frankly, at the level that they would be used to with a wire. It doesn't even take an audiophile often to notice that, right? So our technology brings to the table the ability for someone to take our SDK, run an example on an MCU of their choice, and plug in an audio jack, literally, and then get uncompressed audio, right? Which means it's the same audio quality as you would get on a wire at latency levels that are a few milliseconds, which again is about 10 times better than what Bluetooth latency is. At power levels, power consumption levels that are not going to make your battery sweat, right? And that's the other benefit. It's great for me to tell you all this, but if I told you, hey, bring your car battery next to this, then you'll be fine. You're going to tell me, well, Fred, this is great, but
I would like something low power, please.
Yeah. Exactly. So that's kind of in a nutshell what we bring to the table on audio.
Right. So we talk about audio, but the way I think of it is audio, wireless audio without the codecs is just data transfer, right? So, you can transfer data with this as well.
Yeah, absolutely. So ultimately, this is a datacom device. So you can send your own data throughput up to 41 megabit per second over the air, which typically our customers have gone up to 20 megabit per second payloads, which means it's actually usable data. So that's basically, I would say, at least 10x more than Bluetooth, right? Typically Bluetooth, you're going to have usable data that's sub megabit, right? So and that's what's interesting with the technology. It's a data pipe, right? As low tech as that word sounds, right? It's a data pipe. It has this property of being pretty wide pipe, low power pipe, and really low latency. And then customers use it not just for audio. Actually, audio is one of the use cases, and there's many that we can discuss later today.
Hey, I don't want to wait until later. Can we discuss now? Where else are you finding people using your transceivers?
Well, we found people using it in a lot of different use cases. Obviously, the audiophiles love this stuff. We've got super high-end speaker companies, Focal, Sonos Favor, and others that will come to market for headphones, speakers. This is all about the audio piece, right? We've got gaming companies creating HIDs, right? Mice, keyboards, gaming headsets. Many are not still public, but they're all coming soon. and they're using it for the same reasons, but for data, right? Not audio, obviously, in a mouse. We've got customers in applications in construction sites deploying the technology to track construction workers. They don't care about latency there. They care about the ultra low power of the technology, and they couldn't get it with Bluetooth, right? So that's an interesting use case. That's nothing to do with audio. We have some in robotics where they want to use us in controlling their robots in their industrial floor because we are robust to interference due to some unique capabilities of our transceiver, and we're super low latency. And as you can imagine, in robotics, latency is king, right? The lowest latency, the better your robots, for many reasons. So this is just, of course, I could go on for a while still. There's a lot of use cases, and because of the SDK, it's, I would say, fairly easy to use for a new technology like this. And customers are essentially going and building their own stuff, and some use cases we never envisioned. And we have a few partners that know how to use our technology. Some of our customers say, oh, let me use your partner, and then the partner does the software, or the partner does the hardware, or the customer does it themselves, right? Like any wireless transceiver. So I'd say it's a pretty horizontal technology. Obviously, we can't focus on everything as SPARK Microsystems, so we focus on our own reference designs and in the pieces that you'll see on our websites. But the SDK really allows you to do whichever data pipe you need to do to replace a wire, or to go beyond what Bluetooth allows you to do.
So Fred's being very modest when he's talking about his SDK, because I've told him this previously off camera, but even after like a quick flick through your website, it's obvious that you've actually designed it with engineers in mind. It's so easy to just have some sort of chip that does exactly what you want, but unfortunately it gives you no hand-holding to go out and get using it. And maybe for the old heads, that's how they want it. But personally, all the engineers I know, we would like some assistance, particularly when it comes to high data rate data transfer. So you've got these dev kits, and now you've got your transceiver and an STM32, because you haven't actually got your processor inside of your transceiver, correct?
That's right. So this transceiver has a whole digital interface, but you bring your own processor to the table. Yeah.
Yeah, because I loved looking at it. I just was curious, right? I haven't put this into a design yet, but I was looking at the API calls. And just going onto that website where I could read about the API calls, it was obvious that this is an easy solution to go ahead and integrate. So for that, very well done. Even it came down to you have flow charts. You know those flow charts that you'd always see in university about how to open up a port? It was exactly like that. They made it so easy. So well done for making it approachable. Speaking of making it approachable and designing it in, can you tell me about what a sort of typical journey integrating your transceiver might look like from the first evaluation all the way to production?
Yeah, so we have this SDK, and thank you. I'm sure our engineering team will be very, very glad to hear that. They work really hard.
Pass it on.
And you know this, right? It's not easy to make things easy, as weird as that sounds, right? But thank you for that. So the experience is essentially you would acquire an evaluation kit, right? The EVK. It has a processor on it. It's an STM32 on that EVK, so fairly easy to use processor. It has a transceiver module. We have a few different modules you can pick. And then you can just run the example of the SDK, or you can use a nice GUI that we made that just gives you an ability to test the transceiver quick and dirty. Like you don't have to. You install a GUI, you plug the EVKs in USB, you press start, you see the wireless link happen. You can configure it. You can see, hey, how's my coverage? How's my data rate use case performing? So it allows you, without one line of code, to at least demo what the technology can do, right? With synthetic data. But then typically what customers will say after doing this is, wow, I kind of love this, right? This is exactly what I expected. Then they go into, okay, let me write a few lines of codes, run the examples. If they're an audio company, they'll run the audio examples. If they want to do data, they'll run some of our data profiles. And then they like it, usually anyway. And then they'll go and say, okay, let me make the custom board, right? And then they look at our reference designs. The software team did a great job, but the hardware team at SPARK also has really well documented how you should put this chip down on a board. Ultra-Wideband technology is not trivial to use because it's a fairly high frequency RF technology. So we really tried to make the antenna design and the whole board design as foolproof as possible. And I think we've done a pretty good job considering. And then, of course, they build their custom boards, and then they'll go and they'll build their own applications. And of course, that takes some time. But for example, the mouse customers, we've supported them. They've ported, of course, their mouse softwares. They have their own mouse GUIs and their own features, and they just ported it to our protocol stack. And we're seeing a couple of mouses come out couple of mice, sorry, coming out this year, and a few more next year for gamers. Why? Well, gamers, as you know, they love their latency. Love low latency, love high polling rate. So it happened to be a great fit for our technology, and obviously it's somewhere where these guys expect the chip vendor like us to provide them with a reference design that's robust, right? That they don't have to figure out RF or very intricate protocols, right? These are
I like that.
Yeah.
I like what we were saying earlier. It was about off camera. We were talking about how difficult it is to design wideband antennas. It's so easy to put down a strip of line and make it resonate at a particular frequency, but making it resonate across a band, that's the difficult part, which you actually end up saving people by just giving them essentially a drag and drop sort of shape to make the perfect antenna matched to the frequency.
Oh yeah, we have several antenna designs by now, and we give them away. Like we're not an antenna company, but we understand that if we say, oh yeah, we're not an antenna company, figure it out. No one's
going to do it. Yeah.
An Ultra-Wideband antenna design. And if you go look at commercial antenna designs, unfortunately, it's a newer ecosystem than 2.4 gig antennas. So I would say it's not rich enough yet to fit all needs. We're really happy to see antenna providers start offering ultra-wideband antennas. That's amazing for the ecosystem. But when we started, we just had to offer antennas. And obviously, our antennas are optimized, right? We optimize them for our technology, and you get the best, I would say, bang for the buck when you use our antennas, because it's just a strip of metal on the board that basically costs you nothing, and it does the job often better than an antenna you would purchase, right?
Totally. Okay, I want to talk about some engineering details, and since you're the co-founder and CTO, I think you're the man to talk to. Now, you advertise this IC, and you said before that it's like quite low power, and of course, everything's low power. Do you know what I mean? It's just like a subjective term. So how low power can I truly expect this to be in sleep modes? Because that's where it usually counts the most.
Well, in sleep modes, obviously you're sub microwatt, and in active modes with polling rates that are several tens of hertz, you can be single digit microwatts, right? So I would say that's what I find most unique in our technology. It's very versatile. So you could do 96 kilosample, 24-bit stereo audio, at 10 milliwatts.
Sounds good.
Or you can say, I have this tag. It needs to run for a year and a half, but I want it to send 10 times a second, right? 10 hertz, a polling, right? So that some anchor somewhere in my building catches it and knows where it is. And you'll be able to do it with the same chipset, but it's going to be kilobit per second, right, in microwatts. So you really have I would say, low power for us means low power at a given data rate, and we're always going to be low power, but obviously it's relative to whether you're sending 6 megabits per second or 1 kilobit per second, and it scales perfectly linearly, which is also unique to ultra-wideband impulse radios. They scale linearly with data rate on power consumption, which makes them very interesting that way, because you don't need to pay the price of higher power than you need, right? So you just pay the price of the data rate you need, and there's basically a straight line of power consumption versus data rate. And the lower you go, the lower power it goes. And as I mentioned to you, it could be down in the single digit microwatts. And if you go to the max, well, I call it 10 milliwatts plus or minus, right? Gives you a perspective.
What about the TX currents? Now, I know there's lots of things that go into this variable here. Now, obviously, you've got your transmission power and your data rate overall, but sort of what could I roughly expect to be a TX current? And the reason I ask is, can you power something like this off a coin cell, for instance, a low drive battery?
Yeah, like the TX currents are single-digit milliamp. If you go, 100% duty cycle, which obviously if you're using a coin cell, you don't need to run 41 megabit per second, right? 100% duty cycle would be a 41 megabit per second tag. That's probably overkill, but
probably, yeah.
But usually if you use a coin cell, you're going to be okay with sub 1% duty cycle. So the actual charge. We talk about charge when we talk about these ultra low power applications. It's more about the charge you need to initiate a link, the charge you need to start up the radio, right? The charge you need to send a bit, the charge you need to receive it on the other side, or to receive the acknowledge if you want to use an acknowledge. So We are best in class when it comes to the charge you need to start the radio, initiate the link, exchange data, go back to sleep. We're very confident about what I just said, and that means that if you use a coin cell, as I just mentioned, customers come to us just because they can run us on a coin cell at much higher polling rate than other technologies for years, right? And that alone is a selling point for them. Not all the reason why the audio guys come to us, right? So yeah, and what's I think important also to note, and we haven't explored this space because it's too far in the future, is the energy harvester space. We've done some demos just to see this this super low charge requirement for this radio. What can it build? And we took, a Sharp calculator solar cell. Probably some of your audience is too young to know what a Sharp calculator is, but
now, I'm going to be totally honest with you.
Calculators, right?
I am that too younger audience. I don't know what that is.
Well, the engineering calculators back in the day had a very small solar cell.
Oh no! I knew about that. Yeah, no worries.
And that was like microwatts of power from indoor lighting, but that was great because the calculator would work no matter what, as long as you had indoor lighting, right? And we said, what if we do this with our chip? And we were able to get a really high activity rate sensor that had no battery in it with that small of a solar cell, right? And if you do the math, Bluetooth needing 20x more charge to do the job, well, you take that solar panel, you scale it 20 times bigger, it doesn't feel as cool, right? To need a solar panel that's 20 times bigger to do the same job as Spark. So the reason I say it's future, and I'll end here because I'm going on a tangent, is I don't think energy harvesting is quite there yet with regards to customers' mind. I think there's a lot of amazing wireless technology, energy harvesting technology out there, but I think wireless technology needs to catch up, and we think we have the right chipset for it, but I'd say we're not focusing on it right now. Hopefully someone, though, will hear this and think about it and see if that's the right technology to match with energy harvesting technology.
Amazing. So that's what's sort of in the future for Spark.
That's one of the things we think in the future could be of value because of that low charge budget, right? We don't need a lot of coulomb to do the bit transfer and to start up the radio. It's not even about amps, right? When you have these really energy constrained systems. Yeah, you're looking at every electron,
I'm counting them as they come past me. I was going to say before, this is what amazes me about this solution, right? Oftentimes you will either have a high power, high data rate solution, or you will have a low power, low data rate solution. And it feels like, as long as you're not lying to me, you've got a whole spectrum there.
Yeah, I would say that's the promise of the technology from the beginning. It's always easier said than done, but now we actually have technologies in market that are at the extremes of those, of those data points that you mentioned, and that's, we have these super high-end speakers. Obviously, they stream very high data rate because they want to have pristine audio quality, right? Several megabits per second. I think close to 10 megabit per second for some of those units. And then we have these small tags that are sending kilobit per seconds at best, right? So same chipset, very different power consumption properties. I don't know of any technology. Look, I don't know all of the technologies on the planet, but I'm pretty sure that's fairly unique capability of this technology to be versatile that way. So if you use the technology in one project, maybe tomorrow you'll have a completely different project with completely different metrics of performance that can still use this technology optimally. And that's what I find interesting about it. It's not a one-trick pony technology,
Well, I think this has been a fantastic conversation, even serving as an entry point for people to go ahead and have a look at your transceivers, which I personally will do. I'm going to go ahead and purchase one, but we're going to have a write-up on IPXchange.tech. You can go check it out for Spark Microsystems, where you can apply to evaluate a technology like this, get your hands on it if you have a really cool application. Other than that, Frederic, thank you very much for joining me in the studio today.
Thank you, Elliot. Appreciate it. It was a great time.